This is Trevor Cox. He's a professor of acoustic engineering at Salford University. One of the things he specialises in is filming objects that make sound and then slowing the video down hundreds of times. This camera records at 1,000 frames per second. That's 40 times faster than a normal camera, allowing Trevor to watch the footage back in super slow motion. At this speed, it's possible to see how certain sounds are made and how certain materials react to sound. This camera can't record sound. Trevor explains why.
When you do a slow action replay, the sound on the video goes down in frequency. And we're playing these videos so slowly that the frequency is below where you can hear it. So there's no sound on these videos.
Here is sound and vision at normal speed. And slowed down to 2 times. Then 5 times. And 80 times. The following lesson starters all look at different properties of sound.
I've got some objects with me which make sound. A tuning fork. A triangle. A cymbal. A glass with water in it. And finally, a guitar.
Let's see that again, in slow motion.
I've got here a generator to make a sine wave, some noise, and that's fed to an amplifier and into a loudspeaker. I'll just turn it on.
Once Trevor has set the noise generator to the right frequency, he holds a bubble in front of the speaker to see the effect that sound has on it.
Look what happens when I turn the loudspeaker down and then up. Let's try some candles now. So here's a slightly more dangerous demonstration. What I've got here is I've got a signal generator to make some noise, goes to an amplifier and comes out this rather strange looking loudspeaker. So let's put some sound on.
For this experiment, Trevor needs to generate a specific frequency. He puts little bits of paper on the rim of the glass and he knows when he has reached the correct frequency when the paper jumps off the rim. As with all experiments dealing with loud noises, ear defenders should always be worn. Here it is again in slow motion.
Sounds are often represented as waveforms, which can be seen on oscilloscopes. See what happens when I play a middle C. And if I go an octave higher, and I go right to the top of the instrument. Like a lot of acoustic engineers, I also play a musical instrument. So I brought my saxophone along with 3 others. And on each instrument, I'm going to play the same note. Soprano saxophone. Alto saxophone. The tenor saxophone. And finally, the baritone sax. Here at Salford University, we've used all our acoustic knowledge to make one of these. A confusophone, something that mixes your left and right ears up. And it tells us something about our hearing. Now, to do this demonstration, I need a volunteer. Paul, do you mind putting your blindfold on? And will you put the confusophone on? What I'm going to do is I'm going to play Paul a sound. And I'm going to ask him to point at where the sound seems to be coming from. We're here in Manchester, we're waiting for a thunderstorm to arrive. You know what thunderstorms are like? You see the lightning before you hear the crack of the thunder. And that's because the speed of sound and the speed of light are different. What goes on when something goes faster than the speed of sound? you get a sonic boom. And you can make a sonic boom with a whip. Watch this high-speed video of a whip being cracked. I'm going to play you a couple of notes on my saxophone in this room, which is made up of very hard brick walls. And in this special room, we have foam wedges on the walls, the ceiling, and even the floor. And things sound a little different.
Take a look again at these two rooms made from two different materials, brick and foam. Of course, you don't have to own a musical instrument to make sound. In the lab, Trevor and his assistants often use anything that's to hand, sometimes literally. Take a look at this high-speed footage, and in each case, consider how the sounds are made.
Did I last long enough? I'm out of breath.